Hello everyone, welcome to part 2 of the Hidden Markov model series. So in this tutorial, we are going to talk about the solving the evolution problem. So we talked about three problems before. So this is going to be the first problem that we are going to solve. Now this problem can be solved in two ways. Number one is the brute force way. So it's the easier naive way. And number two is using the forward backward algorithm, which is a little bit more complicated, but it is much more efficient. So let's dive in. So first of all, this example we saw in the previous part of this series, and I've given the link in the description as well. So you can check that out if you are new to this video series. So we have these three different types of states, Q1, Q2, Q3. So these are different stages of cancer, early, mid, and late stage. And these are the observations. So we can actually see a low tumor burden, a moderate tumor burden, or a high tumor burden in the patient, and we can denote them by V1, V2, and V3. Then we have the transition matrix. We have the emission matrix, which talks about the observations given the state itself. And we have the initial probabilities. And finally, we have the HMM as N, M, A, B, pi. So consisting of all of these things. And we have the parameters. Parameter or the HMM model itself, which is consisted of A, B, and pi. These matrices and these probability values, right? So we also saw this particular instance of one sample sequence. So the hidden states, which are the cancer stages, are given, and also the ctDNA or tumor DNA levels are also given as the observations. So the first thing we need to know is how we can calculate the probability of this entire sequence, and we saw it in the previous part as well. Just to summarize, we get all the probabilities for the observation, the transitions, and the initial probability, and we multiply all of them together. So if we understand that, then this is basically the building block of what we're going to discuss right now, the forward-backward algorithm and the naive algorithm as well. So let's first understand the evolution problem. So the evolution problem states, what is the probability of a sequence of observations given the HMM model lambda? So it talks nothing about states. The only thing it talks about is the observations. In short, just to give an example, we saw three observations previously, low, moderate, and high ctDNA level, which are denoted by V1, V2, and V3. So maybe you have tested this patient each month for 6 months. So this is for month one. In month one, we observe V3, that means high ctDNA. Then in month two, V2, month three, V2, month four, V1, and so on and so forth. So what is the probability of getting this observation given lambda, which is the HMM model itself? That means those probability values and all of those things. So this is the problem we are going to try and solve in the first problem. So the naive way of doing this is we calculate the probability for different sequence of hidden states. So basically the thing is we don't know which hidden states are here in the 6 time steps. So we can actually put all different combinations of the states and calculate probability for each one. So in the example before, I showed an example in the previous slide to you where I calculate the probability of the hidden states and the observations. So that is actually the way you can get these different P's. So the first one, the first possible sequence, Q3, Q3, Q2, Q1, Q2, Q1. I'm just making this up. You could have put this in like some other order as well. The probability of that has been given in the previous slide, as I showed you before. So in the same way, you can actually put different permutations of these Qs and you can calculate the P's. So how many different combinations are possible for these sequences? So it's 3 to the power 6 because there are 6 time steps, and in each time step there can be one of these three states, one of these three hidden states. So it is going to be 3 to the power 6. If you add up all these probability values, you are ultimately going to get the answer of this. So it seems quite reasonable and quite easy. But the thing is, this is a try example, and in real life you can have many more states and many more time steps. For example, if you have only 10 possible states and your sequence length is around 50, then you are going to have 10 to the power 50 chain multiplications. So you know that for getting these p's, you require chain multiplications and you need to do an exponential amount of them. And that is not feasible, definitely. So anything that is exponential, we don't want to do that, right? We want to keep things to polynomial. So that is where the forward algorithm comes into play. So let's look at the forward algorithm right now. So first of all, we have the observations and we have the states. So I have basically made some abbreviations here for my own sake. So observation low, moderate, and high are denoted by those small letters, and the states are denoted by capital letters. Okay. So our goal here is to find the probability of seeing a high, moderate, and moderate CTDNA level given lambda. Okay, so obviously this is a toy example, and I'm just showing you 3 time steps and 3 observations. It is because otherwise the example is going to become too big. So hopefully it will clear things up for you. So first of all, we are going to introduce a extra variable, which is alpha in this example. So the forward algorithm requires this extra variable, and let me explain what this means. So you fix a state Si at time step t, and you don't really care which states are there in the previous time steps. So you basically say that I've observed these observations O1, O2, O3 up until OT from time step 1 up until time step t, and also I have seen state Si at time step t. So what is the probability of actually seeing this? So this is the problem. This is the probability value that is going to be stored at alpha. Again, I'm going to remind you of one thing. We don't really know what state is there in O1, O2, O3 up until OT minus 1. There can be any state and any combination of state sequence. We only fix state Si at time step t. That is the only thing we fix about the state. So we have to calculate all these alphas time step by time step for each of our states. Let me explain with an example. So first of all, let's start with time step t1. So the first time step. You can see the different hidden states E, M, L. E is early stage, M is mid stage, and L is late stage, cancel. And H, as I mentioned here, is the first observation. So first of all, we have to get alpha 1. That means alpha for time step 1 for the different states. So alpha 1E is equal to probability of E, because this is the initial state, initial time step, so there will be an initial probability into the probability of the observation given the state, H given E. Same thing goes in all the other cases. And this is basically the base case for the forward algorithm. So the base case for alpha for the first time step is given by this formula, which I written down here. In the next time step T2, we have to again get the alpha 2s for time step T2, alpha 2E, alpha 2M, and alpha 2L. I'm going to describe how we can get alpha 2E so that you can understand the other ones as well. So you know that in this state, in time step T2, we can actually come from any one of these 3 states, because any one of these 3 states can appear in the first time step, right? I mean, we cannot really fix anything here. So it's very simple. We have to take into account these alpha values, and we have to take into account the transition probabilities from these previous states to the time step 2 state, which is E, right? Also, the last thing is we have to take into consideration this observation M. So you can clearly see in this formula that we have taken into consideration the alphas right here, then the transition probabilities right here, and finally the observation probability right here at the very end after adding these 3 things up, because these are the 3 branches. We have to add these 3 things up and then multiply with the observation. That is the basic fundamental knowledge of probability. So you can do the exact same thing for this particular state as well in time step T2. And you can clearly see that we are again using the alphas, we are again using the transition probabilities, and we are again using the observation with respect to the current state M, which is the M. So we can do the same thing for L as well. So this is how we can get all the alpha 2s. Very simple. There is nothing complicated here. And alpha 3, you can guess, is the same thing. We have to take into consideration the alpha 2s, the transition probabilities, and the observation M. That is exactly what we are doing right here. So we can, in the similar fashion, get the alpha 3s in T3. So the moral of the story is, if we want to calculate alpha t plus 1 in a particular future, we have to take into consideration the alpha t's from the previous time step, the transition probabilities. We have to add those multiplications up and multiply with the observation probability. So I mean, I could have shown you this formula at the very beginning, but that will actually mess things up because you would not really understand what's going on in this complicated formula. Now that you have seen some examples, you know exactly what's going on here. So now what are we going to do? So in the alpha 3s, we actually know exactly all the possible combinations of the states. And so the next thing we can do is, in order to get the evaluation of this HMM, high, moderate, and moderate CTDNA level, we can simply add these 3 alphas up, and that will actually give us the answer. So the formula is this. So it's actually the same as what we did right here for the t time steps. Okay, fine. Now that you know how the forward algorithm works, so this all this alpha and then summing up those last few alphas, we need to actually analyze the time complexity of this. So as you can see right here, this is the entire lattice that we created using in the forward algorithm, because first we get these alphas, then these alphas, then these alphas, and finally the alphas in the last time step. And you can see that this is like a nested loop. This is like a nested loop of states. So the time complexity is big O of n square. And this nested loops has to be done for t time steps, and so the multiplied by t. So t is not that important, but the n square part is the most important part. But you remember that previously in the naive algorithm, we actually had to incur n to the power t, right? Time complexity, which is exponential, and this is now polynomial. So that is great. So we have successfully achieved our objective. So if you know the forward algorithm, you can now evaluate any combination of observations for any HMM model. So what about the backward algorithm? So backward algorithm is something you don't need to know in order to evaluate the observation sequence, but you need to know backward algorithm to be able to train your HMM model. In the HMM model training, we need both the forward algorithm and the backward algorithm in order to train the HMM basically. So I will also cover the backward algorithm in this video, but if you are not interested in HMM training, you don't really need to go through that. But if you are interested in HMM training, which I am going to cover maybe one video afterwards in the later part of the video series, I will refer back to this part of the video. Okay, so this is one application of the forward algorithm. The other part of other application is to identify sample family. So I'm going to give you a simple example. So, in the real world, you have different families of protein sequences, right? Suppose you have 3 families of protein sequences, and PFAM actually is a kind of database which keeps track of these families. So for family 1, you have constructed an HMM model. For family 2, you have constructed HMM2. For family 3, you have constructed HMM3. Now, if someone throws a protein sequence at you and asks you to actually say like which family of protein these protein sequence belongs to, then you can actually evaluate that protein sequence using each of those 3 HMMs, and the one with the highest likelihood will be assigned to that family of the protein sequence. Okay, so this is one of the ways, simple ways that this evaluation can be used. Another thing is the outer detection. So for example, if you have a sequence database and you have constructed an HMM model based on that database, and suppose you have a new sequence now coming in, so you can basically use that HMM model on that sequence to evaluate that sequence of observations, and based on the probability you can decide whether it is an outlier or not. If the probability is very, very small, probably it is an outlier and it doesn't belong to a sequence database. So those are a few applications of the evaluation problem. So now we are going to talk about the backward algorithm, which is required in the training process of HMM. So same example as I gave before, but only this time we are going to do something a little bit different from what we did in the alpha variable. In the alpha variable, we looked at all the observations before, right? So we have fixed the state Si at time step t just like before, but instead of looking at the sequences that come before the time step t, we are looking at all the observations that come after the time step t, right? That is the thing. That is the only difference here. So the first thing we have to do is we have to start from the end. We have to start from T3 because we have 3 observations. We have to start from the last observation, and gradually we are going to move to the second last and then to the first one. That is why it is called backward algorithm, because we are moving from the last time step to the first time step backward. So in the very last time step, we have to initialize the beta 3 values for each state as 1, because nothing is coming afterwards, because it is the last time step and it is the final one. So we initialize this with 1. This is the base condition of the backward algorithm. Then we move on to the previous time step T2. This is the T2 time step. So if we want to calculate this beta 2e, we know that this state in the time step 2 can transition into one of these 3 states in the future. So we have to calculate the probability of all of these. So we take into consideration these beta 3 values right here. We also take into consideration the transition probabilities, these arrows, and also the observation probabilities for each of these future states. So you can see right here, and we add all of these things up to get beta 2e. In a similar fashion, we can calculate all other beta 2s. And then if we look at the first time step, again it's similar. We can transition to the second time step from this state, and that is why the arrows are here. In a similar fashion, we are going to use beta 2 values right here, the transition probabilities shown right here, and the belief, right, the observation probability that we show right here. If you multiply those things and add those things up, we are going to get beta 1e. Similar fashion, we can get beta 1m and beta 1l. So the formula is like this. So I didn't show you this initially because otherwise it will complicate things. So now that you see this formula, I think it is very clear now how this is coming by because of the example that I just showed you. So this is the algorithm we are also going to use as a building block for HMM training. So if you like the video, feel free to subscribe and share. And there's a donation link in the description. Feel free to donate there as well. Thank you very much.